Last lecture, we went through an example problem, a simple one-dimensional motion example of dropping a ball. We've actually got all the tools we need to describe our motion in one dimension. We're going to move on to more general sorts of motion, starting with motion in two dimensions. So we're free to move not only in X, but also in Y, whereas previously we've only been moving in straight lines. Now we can describe motion in the entire plane. And to do that, we're going to need a little bit more math. We're gonna have to figure out how to use what are called vectors in two dimensions. We've mentioned vectors before in the course. Today we're going to go through a little more formal how do we actually do math with them. So what are vectors? Well, vectors are quantities that have magnitude and direction. So the common example that I think causes a lot of issues is the concept of speed versus velocity. Speed is what we call a scalar quantity. It just has a size. So you can be driving north at 50 miles an hour, west at 50 miles an hour, south at 50 miles an hour, any direction at 50 miles an hour, your speed is 50 miles an hour. Velocity in physics is a vector. It has that magnitude and direction. So each of those quantities, 50 miles per hour north versus 50 miles per hour west, have different velocities because the velocity, the vector, includes that direction. So scalars, just some number, some magnitude, whereas vectors have that magnitude as well as a direction. So far in this course, we've been using this geometric representation where in our motion diagrams, we would just draw arrows representing the velocity and the acceleration vectors, and the length of those arrows represented the magnitude of the vector, and the direction they were pointing obviously represented the direction that vector was going in. Now we're in two dimensions, they're going to be a lot more useful because one dimension you essentially have two directions. You could be going right or left, up or down, whatever. The two directions on that line you're describing. In two-dimensional motion, you have an infinite choice of directions that you could be describing. So we have to get a lot more detailed in our description of vectors. We also have gone through how to add vectors. In one dimension, if you remember, think back to how we described determining the velocity. If we had a motion diagram that had a velocity vectors that looked like this, where this was v2 and this was v1, and we wanted to know the difference in those vectors, the change in velocity, well, it was simply v2, the final, plus minus v1. And in this geometric representation, well, v2 is just v2, like that, and v1, negative v1, is just the opposite direction of v1, so we would take the v1 vector and change the direction of it like that. And if we wanted to do that addition, what we did was we took we would just add, we started here, went through v2, got to here, added the negative v1, got to here. The resulting vector from where we started to where we ended was delta v. We do the same thing in two-dimensional motion, right? If we have these two vectors a and b and we want to add them together, we just put the tip of the first vector and take the tail of the second vector and put them together. So we have this situation here, and then after that, where we started to where we ended after following that, essentially follow the arrows, gets us the addition of those two vectors. Another thing of vectors we want to pay attention to is that, I don't want to use the word location, but where they are isn't really as important as a lot of students like to think. So the example that I'm going to use is from the book. If we consider two people, Bill and Sam, who get up in the morning, they leave their house, and they walk 200 feet northeast. They both do that. Bill left his house. Sam left his house. They both walk in that direction, the same distance. the fact that, Bill started at his house and Sam started at his house does not change the fact that those vectors are the same. Remember, the vectors have just the magnitude and direction. And in both those cases, the magnitude of that vector is 200 feet and the direction is northeast. And since that's the same for both Bill and Sam, those vectors are identical. They are the same. And when we do, and you think about why this is important, is this relates to how we add. If we wanted to add those two vectors, b plus s, and we wanted to do that tip to tail, we'd be taking this tail of this Sam vector and moving it up to the tip here and adding that vector there. But the point is, where that vector is drawn does not change what that vector is. Another way we can add in that geometrical representation is, let's look at the two general ways we would add two vectors. So we just discussed this. Let's say we have vector E and vector D, and we want to know what is the addition of D plus E. Well, we just discussed doing the tip to tail method, where we go from this starting point, we take our first vector, and on the tip of that vector align the tail of the second vector, and then go from where we started to where we ended, and that gives us the resulting addition vector. Another way of doing this is to do what's called the parallelogram rule. So in this method of adding vectors in the geometrical representation is we essentially align the tails of the two vectors we're adding, and then draw the parallelogram that is formed by those two vectors. And after we've done that, the diagonal through that parallelogram is the resulting addition vector. And you can see how this is the same. I mean, when we do the tip to tail rule, we get this triangle here, and that's the same triangle that's half that parallelogram. So those are two ways to add. Both of them work, they're equivalent. I personally prefer the tip to tail method, and the only reason for that is this sort of situation. Say you want to add more than one vector, or more than two vectors. Say I had 4 displacement vectors that are shown here, where I have D1, D2, D3, and D4, and I want to know, after I've gone through all of these displacement vectors, what's my total displacement? With the tip to tail method, I think it's a lot simpler. You're essentially just following the arrows. You start with D1, you started here, you end up at its tip, then you put the tail of the next vector there, follow it to its tip, put the tail of the next vector here, and you essentially just follow those arrows until you get to the end, and the resulting total net vector is where you started to where you ended, and that gives you your total vector. So how do we describe vectors mathematically then? All right, we've got this nice visual geometric representation where we can sort of see how they work. How do we describe them mathematically? Because ultimately we are going to have to put numbers and do some math with these quantities. The first way we do this is magnitude and direction. So if we think about vectors, we have, say, we'll just call some random vector A and draw it like that. We have that vector A, and if I need to describe it, I need 2 pieces of information. I need to know how long it is, the magnitude of that vector, and the direction. And I can do that just by giving you that information directly. So if I have, let's just draw a coordinate system here. In 2 dimensions, I have the x direction and then the y direction. And if I want the magnitude, I can just tell you, the magnitude of A, which typically one of the notations is just take the vector and put absolute value bars around it, and that tells you I'm only looking at the magnitude. If I did do that and I gave you some angle relative to an agreed upon direction. So once I define this coordinate system x, I can tell you, all right, this vector is, let's say it's a distance vector, is 5 meters and it's at an angle theta above my x-axis. And so now I've given you the theta, that tells you the direction it's going in, and I've given you the magnitude of that vector. Another way I can describe this mathematically is by describing it in terms of what are called components. And what this is doing is essentially it's splitting that vector into two vectors, one along each of the directions of our coordinate system. So we just went through how to mathematically add these. I could take this vector along the x direction, and I'll call that a sub x, and this vector along the y direction, and call that a sub y. And I know that my vector a is equal to ax plus ay, where these are the one-dimensional vectors in those directions. So how I would write this is I would, get rid of these vector symbols on top of those letters and say my vector a is equal to ax in the x hat direction plus ay in the y hat direction, where x hat and y hat are what we call unit vectors. They're vectors of length 1 in the direction of our coordinate system. So these are the two ways I can do it. And notice, in the first case, I'm giving you a magnitude and a direction, two pieces of information to totally describe that vector in 2 dimensions. In the component, I'm giving you the component ax and the component ay. How far or how long is this vector in one direction and how long is it in the other? Both of those describe that vector completely. Turns out they're related, obviously. If they're describing the same vector, they have to be related. And the way we can see that is through trigonometry, right? So just if I redraw that vector A here, and now I have my A sub x and A sub y sides of that triangle, my coordinate system is right angled. So that angle is 90 degrees. This angle is theta from my magnitude and direction description. So if we remember our trig relationships, we have sine theta is equal to opposite over hypotenuse. Cos theta is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent, right? This is the SOHCAHTOA, the trigonometric relationships for right angled triangles, where the opposite is referring to the side of the triangle opposite the angle theta. Adjacent is the side, the length of the side adjacent to the angle. And hypotenuse is the length of the side opposite the right angled triangle. So if I use these trig relationships, I can relate the magnitude of the vector, i.e. the length of the hypotenuse, with the length of either of these two sides. So, we have sine theta is equal to the opposite, which is ay, over the magnitude of the hypotenuse, a. This can, a little bit of algebra says the magnitude of that vector times sine theta is equal to my y component, the magnitude of my y component. Likewise, that cosine theta is going to be equal to the x component over the magnitude of the total vector, which lets me know a cosine theta is equal to the adjacent or the x component. Now, you have to be careful with where you've drawn and be sure you know which angle is actually given. I could have equivalently given you this angle, call it phi, and these relationships would be reversed because the opposite angle would then be the x component and the adjacent angle would be the y component if we're using that angle. So I always recommend drawing the actual triangles and labeling the angle to make sure that you're solving for the right things. Finally, if you're given both components and want to know the angle, you can just use another one of these trig relationships, but you can take the inverse tan or arctan of a, in this case it would be ay over a x would give you that angle theta, because it's the inverse of that opposite over adjacent. Anyway, those are the two directions, the two ways we can describe vectors. We can use magnitude and direction, or we can use components. We can relate those two using our trigonometric identities for right angle triangles, and both are going to be kind of useful, and that's what we're going to need to move on to kinematics in 2 dimensions. We're going to have to take these 2-dimensional vectors, split them into components is generally what we're going to do, and describe the x component and y component separately.